SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We are in the topic of damping, and we said we will connect the equivalent viscous damping coefficient, the material loss factor and the modal damping coefficient. We will see how they are connected. Now we were seeing in the last class how the loss factor is brought in. It is brought in using a complex Young modulus. Okay. So if in the standard equations of motion that we have, if the Young modulus is made complex, okay, and because this is just a constant, it will fall out of this spatial operator. Okay. So the equation looks like this. Now if we follow the same procedure and you represent each individual displacement as now a weighted sum over k 1 to infinity, the participation factor and the mode component in the individual direction. Okay. Then we substitute it back in the earlier equation, then eta k is a time term, the spatial operators does not work on it. So what we have is the summation from k going from 1 to infinity 1 plus j eta k L I u1k u2k u3k minus rho h eta k double dot uik is equal to minus qi star e to the power j omega t. Eta is the loss factor and eta k is the modal participation factor. Okay. So now we know that in your eigenvalue problem we set damping to 0, okay, eta is set to 0 and external force is set to 0. Then what do we have? We have L I working on each modal component gives me minus rho h omega square k uik. We have seen this has been the crux of all simplifications. Okay. So now what happens if we substitute for this as this in the equation here, we will get finally summation over k rho h eta k double dot, we are reversing all the signs now, plus rho h 1 plus j eta omega square k eta k into uik and that is qi star. Okay. Now we again do the same, we multiply this by u, okay, ip, okay, each one of these. So first one has u1k, we multiplied by u1p. The second equation has u2k multiplied by u2p. Third has u3k multiplied by u3p. This part is the same, okay, and this has q1 star, q2 star and q3 star, and then we sum it up, we sum the three equations up. When we do that, we get summation k going from 1 to infinity rho h eta k double dot plus rho h 1 plus j eta omega square k eta k and integral alpha 1 alpha 2 u1k u1p plus u2k u2p plus u3k u3p a1 a2 d alpha 1 d alpha 2, that is equal to, on the right hand side, alpha 1 alpha 2 q1 star u1p plus q2 star u2p plus q3 star u3p a1 a2 d alpha 1 d alpha 2. Okay. And from orthogonality k has to be p, okay. Then one out of this sum is picked up. So what do we get? From here we have eta k double dot after dividing by rho h plus 1 plus j eta omega square k eta k is equal to f k star e to the power j omega t, where f k star, we know this from before, is 1 over rho h n k integral alpha 1 integral alpha 2 q1 u1k plus q2, these will be stars I suppose, u2k plus q3 star u3k a1 a2 d alpha 1 d alpha 2, and the familiar nk is integral alpha 1 integral alpha 2 u1k square plus u2k square plus u3k square a1 a2 d alpha 1 d alpha 2. Okay. Now if we want to solve this, we follow the same procedure. Eta k is some gamma k tilde e to the power j omega t, where gamma k tilde is f k star by omega square k minus omega square plus j eta omega square k. If you remember, this used to be j twice zeta k omega k omega. Okay, now it is this. Okay, so that gives us the equivalence, which is twice zeta k omega is equal to eta omega square k, or zeta k is half omega k by omega eta. Okay. And we also have lambda as equal to rho h omega k squared by omega to eta. Okay. In the simple manner, this is how lambda, the viscous damping coefficient equivalent, the material loss factor, and the modal damping coefficient are related. Okay. Now, with this I will close this series of lectures on vibrations of plates and shells. I would like to make some closing comments. So, as a summary, in summary, what did we do? First of all, let me say this, I have been wanting to say this for a while. The book, or Professor Sodell, he prefers a left-handed coordinate system. Left-handed coordinate system. Whereas my training always has been right-handed coordinate system. Okay. X cross y goes into z. Now, as far as these series of lectures vibrations is concerned, we are using the energy methods. So, let me just put it that it does not matter, does not matter. The shell or the plate does not know which coordinate system you are using. Okay, that is the first thing I want to, because if you look at the diagrams, they are all left-handed coordinate diagrams in the book. Okay, so students may get confused. So, now what did we do in this course? We started by looking at differential geometry, okay, geometry of infinitesimal lengths. Okay. Then we found some relations, most importantly the Gauss-Codazzi relation. Okay. And so, if you can find a surface with Lamé parameters and radii of curvature that satisfy the Gauss-Codazzi relation, then that is a legitimate surface. Okay. That is the theorem. Okay. Of course, mostly we are interested in surfaces of revolution which fall under the category, that is, they satisfy the Gauss-Codazzi relations. Okay. Then we formulated the energies, the potential energy and the kinetic energy in the most general form for any general shell, okay, with Lemma parameters A1, A2 and radii of curvature R1, R2, the Hamilton's law, okay, and we proceeded and we gave out the most general form of dynamical equations, okay. You can use a symbolic software to punch all these equations, and at the top the moment you plug in A1, A2, R1, R2, you will get the specific form of equations, okay. So once these equations were obtained, we looked at several geometries and we obtained the modes and natural frequencies, okay, and we looked at animated forms for some of them, okay. Now once you have the, so this was a first attempt was to find them analytically, okay. Now for several cases it is difficult to find analytical forms, so we did approximate. There we used the Rayleigh-Ritz approximation, okay. So we have modes and natural frequencies at this stage. Once we have this, we can go for the forced response. Within this we talked about transients, okay, how to solve a transient set of equations using initial conditions, okay, through Laplace transforms. Then we went for harmonic analysis, and so here we took a modal force, we took a force, then from there we computed the modal force, from there we computed this gamma mn tilde and then eta mn, and then eta mn and mode shape summation gave us the first response. And we looked at largely plates, rectangular plates, and we applied various types of forces, a point force, a point moment, a rotating moment, a line force, a line moment, okay, a moving point load, pressure, etc. Okay. We said the units have to match, the force units have to match, and it has to be a proper description of the force. We even applied a point force on a cylinder and looked at the response including all the parameters, all mode shapes to a point force. Okay. Then we followed this with connected structures, through acceptance method. Okay, it is a very useful technique. You can do point connections, you can do line connections, okay. You can do voids voids in a material. Okay. Then following this was the last chapter or section on damping. We gave some semblance to this thing called damping, and we presented how the equivalent viscous damping coefficient, the material loss factor and the modal damping coefficient can be connected. Okay, how can be related. Okay. Now the textbook and of course the topic of vibrations is much more vast than what we have presented. Okay, it's just in some way another first level. Okay. For example, you can derive equations for a barrel type system, a barrel. Okay, so cylindrical barrel. Okay, the sides are now curved. You could take A1 to be 1 approximately, A2 to be A. Okay, this A diameter, this diameter is A, I mean this radius is A. Then you can take R1. Okay, let us say R1, you can take R1 to be, R, R1 to be R and R2 to be A. Now you can take R1 as minus R also, then you will get a this sort of a system like a wine glass or something, or an hourglass. Okay. You could study a spherical cap. You can formulate the equations, that is what I mean. Okay, equations of motion. Solving is another matter. Okay, you can either manage to find exact solutions or you go for an approximate method like Rayleigh-Ritz. Similarly, you can look at a spherical cap. Okay, instead of the circular flat disk, you could look at a spherical cap, and there you would again set A1 to be 1 and A2 to be R as for a circular plate, but you can set R1 equal to R2 equal to R, so that you get this spherical effect. Now this is a spherical cap. Okay. So you could find equations for such systems. Okay. Then there are other approximate methods. Okay, or other approximations such as the extensional approximation or the membrane approximation, where in plane displacements are dominant. Okay, in plane displacements dominate. In all these shells, they give you one set of approximations. Okay, then you could have bending approximation, where the in plane displacements are ignored in some manner. Okay. Now if you had a cylindrical shell, and let us say this is the natural frequency curve for the full blown theory, if you used a bending approximation, you would probably match this set of natural frequencies very well. Okay, these are there in the textbook. Okay, the bending approximation for a cylindrical shell. Then there is a very famous approximation called the Donnell-Moshtaré-Vlasov theory, okay, which is for shallow shells, okay, where the radii are much larger, and these are also bending dominated shallow. It is also called shallow shell theory. Okay, it is a very elaborate theory and very useful theory. can give you quick approximations to very common shells. For example, that spherical cap, if you think it is a shallow shell with a radii large, then you could use the DMV, as it is called, DMV approximation, and quickly get resonances. Okay. Now there are green function methods to find dynamics of shell structures. Okay. Then other approximations like finite difference approximations, okay, or even Galerkin methods. Okay. Then you have other types of systems, rotating structures you have. Okay. The rotation gives additional internal stresses. Then you have thermal effects. Thermal effects within structures which also give a kind of a pre-stress. Then you can have vibrations, study vibrations of composites. Okay. And so on. Okay. So there are many topics that are not touched, but I guess the core focus was of how to obtain a general set of equations, okay, for many common systems, okay, and then obtain modes and look at forced response, this connection. So with this I close this set of lectures, and I hope you have benefited from it. Thank you.